All right, here we go. So moving on to part B. Part B is just more manipulations of the log function. So paying attention to our properties, our transformation properties. Our transformation rules and our properties of logs. So when you're graphing a log function, you have that k is your power, right? So if you have a k power or a k on your argument, a power on your argument, it can be expanded because that k can become the coefficient of your log. So it goes, so when you have k, that is your vertical dilation, okay? The power of your argument is your vertical dilation. Does that make sense? So when we look at our example, so we have here log base 2 of x squared. We're going to graph again log base 2. I use log base 2 just because it's easier, like numerically, to graph. It is not the parent function, it's just this parent function I'm going to use because it's easier to graph. So we're going to graph log base 2. Remember, log base 2, how are you late? You're basically absent. So you have your vertical asymptote at 1 is going to always be 0. And for log base 2, you're saying 2 to what power? Or 2 to the 1 power is 2. If I go up here, 2 to the 2 power is going to be 4. Notice that I'm working backwards. 2 to the 3 power is going to be 8. Because a log is the inverse of an exponential. So if it's hard for you to process, remember, we question a log as an exponential. And therefore, we can work backwards. So instead of me starting on the x-axis, notice I was using my y-axis to find my x values. Because I went backwards because it's just faster for me to process 2 to this power, 2 to the next power, 2 to the blah, blah, blah. So as I went along here again, 2 to the 0 led me to 1. 2 to the 1 led me to 2. 2 to the 2 led me to 4. And 2 to the 3 led me to 8. And now I've created my log. Okay, pretend that's good. Yep. Beautiful. Curvilicious. Now I've graphed the parent function. Okay, vertical dilation. So we have g of x equals log base 2 x squared. We're going to write this in expanded form. Expanded form, we're using our power property. The power property says that the power of your argument becomes your coefficient. So we're expanding g of x to be g of x equal to log base 2 of x. So now I have this value. I have my a value and it's greater than 1. So this is a vertical dilation by a factor of 2. Because our y's don't lie, right? Only the x's. All right. So that means to all of my y values, I'm going to do what? So all y values are multiplied by 2. Okay. So for my new points, I'm going to write them out for you. So at 1, it's going to stay 1, 0 because 0 times 2 is still 0, right? Currently, I'm at 2, 1. So its new point is going to be what? 2, 1 is going to become 2, 2 because you're multiplying your y values, not your x values. Does that make sense? All right, we're currently at 4, 2. So 4, 2 is going to become 4, 4. And we're currently at 8, 3. And 8, 3 is going to become 8, 6. So these are the new points that I'm going to graph to show my vertical dilation. So again, 1 is going to stay 1. 2 is now at 2. 4 is now at 4. And 8 is now at 6. This has no impact on my, what's this thing called? Asymptote. Because 0 times 0. 0 times anything is still going to be 0. So I'm going to do my very best to trace my points. And even if I don't, you're all going to be like, good job, Ms. Jones. Thank you. I want you to see the level of concentration that is taking place right now. Thanks. I tried really hard for you. All right. Do we feel comfortable taking the power and converting it to a vertical dilation and interpreting it? Doable? All right. Let's keep her going. All right. Up next is our change of base and how change of base helps us see that what we have listed is also a vertical dilation or a horizontal dilation in chant. So we have currently log base 2 of x minus 1. Well, log base 2 of x minus 1, we know that this is currently a what kind of transformation? Horizontal. It is a horizontal translation. Which way? There we go. Right 1 unit. Okay, it's currently a horizontal translation, right 1 unit, because our x's are liars. So we see that minus like, oh, nope, don't fall for them. Don't fall for those same old tricks. Okay, keep them as an x. All right. You're going to use the change of base to describe how does this change this from a horizontal translation to a vertical dilation. All right. So with change of base, what ends up happening here is that you can separate and turn it into a common log. So I can take this and turn it into a common log. I am not about to graph this again. You get the graph. I'll graph it in the calculator. I don't want to graph again because that was real hard for me. So I'm gonna let Desmos do my graph. I know that sounds lazy, but go with it. We're going to change this to a common log. So we're going to change from this to a common log. Common log just means that I do not have a visible base, but the base equals what? 10. Okay, so even though I don't see it, the base is 10. In order for this to be common log, you're going to take the log of the argument. Do we see that? And we're going to divide it by the log of the base. The log of the argument divided by the log of the base. So that ends up looking like this. Log of x minus 1 divided by log of 2. When you have a division problem, it can be written as a multiplication factor. So this is the same thing as 1 over log of 2 times log of x minus 1. A division problem can be written as a factor of a fraction. Does that make sense? So now, instead of it being a log base 2 horizontal translation, is now a common log that is translated and dilated. Does that make sense? Do we see that? Okay, that's why I said I'm going to do this one in the handy dandy calculator. All right, here's our parent function, the red guy, right? Then we're going to have our transformation. So our transformation is y equals log shift 2, not z, of x minus 1. And that's a translation, right? Now, we're going to write it as a change of base with common log. So we have y equals, and I'm going to have log of x minus 1 divided by log of 2. And what do you notice happen? It's the same. It's wizardry. Yes. So when you are dividing by 2, it's the same thing as multiplying by half, right? Same thing here. If I'm dividing by log 2, it's the same thing of multiplying by 1 over log 2. So notice when I write y equals 1 over log 2 times log of x minus 1, what happens again? It's the same. It all is the same. It's just a different way that it appears. So that is why when you have a log of any base that is a horizontal translation, horizontal translation, if you use change of base, it's going to become a common log dilation with a translation. Does that make sense? All these are equivalent forms. To show you that all the properties are tied together and that they all work together and that math is magical. Okay? It's the closest to being a wizard I'm gonna get. So welcome to the ride of it all. All right, so what's happening here? When you look at these values and you're taking it as a log, one, which is easier to manipulate? The initial version, right? The translation. It's easier for me to just take my points and shift them all to the right one unit, right? Uh, Great, love it for you. But if I have a problem and I'm trying to simplify or solve something, and I do need to change the base, then it allows me to put everything on the same base or combine like terms. Does that make sense? Because what if you have log base 3 of x plus log base 2 of x? Can I combine them? I cannot, because their bases aren't the same. So, but once I change their bases, then could I combine them? Yes. So that's where that would come into play. That's where that would come into play, okay? All right, but equivalency, do we see it? Remember, this is why I didn't want to graph it, by the way, because sometimes you just need to see the visual of it. All right, I know it's some sorcery happening here, but so describing the change in the output values. So when you're looking at the output values of log base, and again, this could also say log base 2. If it stayed log base 2, then it would just be repeating itself. That's why you wouldn't keep it log base 2, because you'll be divided by 1, which is why am I doing that, right? That's why we use the common log to show that change, all right? When you are changing it, you're now looking at it completely as log, like the log function. And for the log function, you're manipulating it. So what that would be looking like mathematically is once I've done this, I'm now taking log base 10. So you're manipulating log of x, which is your common log. And with the common log, what's happening is for your x values, you're adding 1, right? If I need to go to the right. And for all your y values, you're dividing by log 2. And that's how that shift will happen. See it? Do we see the pattern? Somewhat. All right, so just to test this out, what if I had, I'm going to write it out, make up a number to see if you can catch on and tell me what it would look like. Log base 3 of x plus 2. If I wanted to write this as a common log transformation, what would it look like? What would be the changes to my x's? There we go. And then, bam. So you don't have to call that all the extra steps once you know. Once you recognize the pattern, then you could just manipulate the values. Do we see the pattern between the two? Okay, so once I know this, I know that I'm looking at this, and if I'm graphing a common log, I know that all the x values are going to subtract 2, and all the y values are going to be divided by log 3, which is why, as a common log, it represents a translation and a dilation. Okay? All right, all logs are tied together. All right, do you think the rules are going to change just because I have natural log? Probably not. You're so smart. They do not. Okay. Just because you have natural log, nothing's going to change. The only difference is that it's ln, and that's because natural log is your log with base e. That's all natural log is. I used to call it log in high school. Natural number, e is like pi. It's a number that shows that something can infinitely and continuously happen. Just like a pi represents the fact that circles can keep going and going and going, right? E is the same thing. We can keep growing or we can keep decaying. That's what's called the natural. E is the placeholder for anything that is growing continuously at every moment, every second. Yeah, that goes on. It's a repeating decimal that goes on forever. It's not just a variable, it's a value. Just like pi is a number that goes on forever and ever, e is a value that goes on forever and ever. That ties to log and exponentials. Okay. All right. So we call it our natural base. So e is our natural base. So when you have log of your natural base, we write it as ln. So the properties are going to be exactly the same. All right. So natural log, it's the same function, it's just that it starts at like 2 point something, which I can't think of at this moment, but it's 2 and some change. So finding the domain, your domain is still going to be the same unless you are shifted. Okay. Your domain depends on your horizontal translation. If there is a horizontal translation, your domain is shifted. Does that make sense? Exactly. That's the start of our domain. I have a horizontal translation, right? That horizontal translation is 1 unit to the left. Because of that, that means that my domain starts at -1 and then continues to infinity. So as long as there's a horizontal translation, your domain is going to be shifted. That's the only thing that's going to affect your domain. Capiche? All right. All right. Next, state the range and asymptote. So your range, guess what? Never changes. Your range is going to always be all real numbers. That's what your range is going to be, because you're going to forever going down and forever going up for all log functions. Just like exponentials is the inverse, right? Your domain is all real numbers. And this time your asymptote is a vertical asymptote. And it's going to be at x equals -1, which is why your domain starts at -1. Okay. For all parent functions of logs, if you have natural log of x, your initial intercept is going to be at 1, 0. All of them. Everybody's intercept is going to be at 1, 0. That's natural log. Well, this was transformed, right? So therefore, these transformation rules have to apply to this. So the transformation rule that is being applied here is what? I need to shuffle, translate -1, 1 unit left, and then I would be multiplied by -2. But is that going to change my 0? No. So for this transformation for f of x, where is my y-intercept? It is at 0, 0, because I had to move 1 unit to the left, which also makes it my x and my y-intercept because I'm at 0, 0. All right. Now, function behavior and concavity. What affects your concavity is your A value. Your vertical dilation is going to affect your concavity. So you're looking at your vertical dilation. If your vertical dilation is greater than 1, then you're going to be concave down. If your vertical dilation is less than 1, then you're going to be concave up. Does that make sense? In our case, our vertical dilation is what? It's going to be less than 1. Well, not less than 1. I'm at 0. I'll just let me say 1. But you get what I mean. If it's positive or negative. It's going to be, what's this guy? Concave up. Makes sense? And that's because it is reflected. So our end behavior, our function behavior is, it's doing this number. This is not going to be drawn to scale, so accept it. I could at least gone through the origin. I'll be better. I'm going to fix that. So it's 1, not 0. I said I was going to fix it. I could have at least, followed and pretended. That's close. Oh, that's not bad. Not bad at all, Shauna. As long as I went through the origin and I didn't pass my asymptote. And this is because it is negative. So describing your behavior, you're saying as, you're going to write it as limits. Okay. So we know that we're concave up, concave up.
Wait, it has to be less than 1.
Yeah, that's why I said I messed up there. Yes. I said it when I was talking. It needed to be negative. All right. So limits. When you're describing end behavior, you have to write it in limits. When there's an asymptote, you're going to address that asymptote. We write our limits from the left to the right. So our left-hand limit. So on the left, the limit as x goes to -1 from the right. That's what that means. The limit as x goes to -1 from the right. What is it doing? F of x equals what? Where am I going? Positive infinity. So the answer would be positive infinity. On the right-hand side, what am I doing? The right, the limit as x goes towards positive infinity, f of x equals negative. And that's what it's expecting when it says to write your limit behavior. You're going to write your end behavior, you're going to write it using limit notation. Okay? If there's a vertical asymptote, you're going to always have to state, are you coming from the right of it or from the left of it? That's what that little plus or minus subscript means. I'm coming from the right of it and heading towards positive infinity. Huh? Oh. Does that make sense? All right. Here's the true test of can you describe all things on your own? You have to do it by yourself. So here is your g of x. You have g of x equals the natural log of 3 minus x squared, tying together everything we've said. And what's happening? Find the domain, state the behavior, and go. I believe in you. All right, so let's look up here. When we look at our equation, we start off with natural log of 3 minus x squared. I know that squared is actually my coefficient. And natural log, I need to factor out so that my x is positive. So I'm going to divide everything by -1. So I factor out that -1, and I'm left with x minus 3. So that is my fully... Huh? Oh, I don't know. What are you talking about? There's been a 2 there the entire time. Yep. Okay. So after you have fully put it in its transformation form, where does your domain start? At 3. And then continues to positive infinity. Your range is still going to always be what? All real numbers. And where's your asymptote? Three. Remember for a log, your asymptote depends on your horizontal translation. And my horizontal translation is 3 units to the right. What starts at 1, 0? The paired function, yeah. I'm not on intercept. I said asymptote. I said asymptote. I was like, I didn't ask for that. But yes. Okay. Now let's talk about intercept. So your intercept, remember the parent function, natural log of x starts at 1, 0. So for our g of x, we have some transformations taking place, right? So to our 1, we're doing what? We are adding 3 and dividing by -1. Okay. So what? Let's look at it on a graph. Y'all give me faces. I don't like the faces. If I was a graph, where would I be? Right here. Right. Do. I'm going to finish this so that it'll be fully recorded. Natural log of x looks like this. We had y equals natural log of x minus, I'm sorry, 3 minus x squared. Okay. Yes. Is what? Next week. Next week I'll update it. I shall update things, I guess. Huh? We didn't get to do it. I'm just gonna adjust. I gotta adjust our lives. Yeah, I have to adjust our lives. All right. No, you don't. Toodles noodles. All right, so now we moved our power, we factored out, and as you can see, where we write about our domain, we're not write about our domain because what happened on the horizontal? It reflected. So our domain is actually from negative infinity up until 3. It is.
But I didn't know why. I just that's all it was.
Yes. So our going back to what we had, we're like, oh, it was reflected because we did not pay attention to the fact that our -1. So now we're at negative infinity to 3, which is why our intercept is now at y erase. Why not be like, hey, miss? See? So now we have an intercept at 2, 0. And we also have a y-intercept. So we have two values that are at play. We have two intercepts. We have an x-intercept, and now we have a y-intercept because we were reflected. So we now have both of them. Okay?
And it's 2 and 4 cut to the square, right?
Mm-hmm.
Okay. I ain't taking it to the count. Square.
So we have 2, 0, and we were at